A list of paper. I selected many good papers. I'm going to complete this, add 10, 20 more papers to this. And I try to categorize them in different categories in terms of application or theory. You're going to see important papers in this field. Some of the papers are like color-coded by blue. Means those papers we definitely, because we cannot read all of these papers in class, but those papers that are blue are papers that we definitely want to read. So make sure that those blue papers are selected. So the way that we are going to organize the second part of the lecture, which would be mainly paper presentation, is through this wiki course note. If you had a course with me in the past, most likely you have an account on wiki course note. But if you don't, if you just type wikicoursenote.com, you will get to this page and you can see the course note of my courses in the past. But to be able to participate and contribute on the content of wiki course note, you need to have an account. So just press login, and then you don't have username and password if you are new. If you have it from the past, it's still valid. But if you don't have it, just request one. And then there's a couple of information that you need to give me, username and email address and so on. And then request account. So then I get an email from you and I approve it, and you're going to have an account. When you choose your username, make sure to choose your UW username, and make sure that you give me your UW email address. Don't give me Gmail or Hotmail or whatever. So make sure that this is your UW email address and this is your UW username. Otherwise, in terms of marking, it's going to be difficult. I have a hard time to match who is who. Okay, so suppose that you have account on wiki course note after you made your request. You are going to have an account on wiki course note. Then you are going to see, there are many pages here. You are going to see a new page on deep learning. We are going to use that page for paper presentation. So you're going to see a table there, and it works like Wikipedia. When you have an account, you can edit it. So you're going to see a table there, and you have to register the time of your presentation and the paper that you are going to present. So you're going to select one paper in the list of papers that will be posted on my web page, and you're going to register on a particular time that you want to present this paper. Okay? That's about the time of presentation. I'm going to teach about half of the course, like about 6 weeks I'm going to teach, and after that, roughly, we are going to start presentation. So the rule for presentation is that ahead of time, before presentation, and I'm going to specify the time for that, you have to, as a presenter, you have to write a summary of the paper that you are going to present on this wiki course note. So we want to present paper A, say, for example, 1 week before the presentation, you need to put a summary of the paper that you want to present on wiki course note. Everyone else who register for the course officially needs to contribute on this summary before the presentation, okay? Before we come to class for presentation. So 1 week before the presentation, the summary is there. You have 1 week to contribute on this summary. So it means that you have read the paper before you come to the presentation. And I'm going to give you the detail later on, but the contribution could be different type of contribution. It could be technical contribution, or it could be editorial contribution. So we're most interested in technical contribution, of course, but you may not have technical contribution on all papers, but you need to have technical contribution of a good portion of the papers. So you can, add an example, elaborate on some concept, give reference to another paper which make it more clear, provide a piece of code which make it clear, something, a technical contribution or editorial contribution. Then we come to the lecture for presentation, so we know that everyone has read the paper before that. So that's basically how our paper presentation is going to work, and your contribution has a portion of the mark, and also the summary that you're writing has a portion of the mark, and your presentation has a portion of the mark, which altogether makes about 50% of your mark. And I'm going to specify exactly portion of each part and post it. Any question? Yes?
So to get any information on the course, we should use the Piazza site, not Learn?
Yes, yep. Yes, I'm going to use Piazza for announcement. I'm going to put this list of paper on my own web page. So if you go to my web page under teaching, there's a deep learning. And on deep learning page, I'm going to put this page there. Yes?
So for people who are just sitting in the class, can they also request an account on this, or is it just for those who are taking it for credit?
It doesn't matter if, they can do. I mean, without account, you can see everything, But you can't make contribution. If you want to edit, if you want to change something, you need an account. If you're just sitting in the course and you want to have an account, that's sure, no problem. It's just password protected because we are using this for marking at the end. And, this has a history, so I'm going to look at the history. I'm going to see who has done what was your contribution in the summary that we are seeing now.
So
yes?
Is the summary a collaborative summary?
Presenter has a summary,
Okay.
but everyone else are going to collaborate and contribute to it. But looking at the history, it's going to be clear who did what, What was your contribution in this? Eventually, it's going to be a collaborative summary, but for marking, I'm going to check the history to see, contribution of each person. Okay. Any other question? Yes.
I think you can contribute on more than one paper.
Well, you have to actually. You have to contribute. We're going to we are going to have 24 papers for presentation. And again, roughly, you're going to contribute on about 20 papers. You're going to write summary of one paper and contribute to about 20 papers to have the full mark of that.
For each week?
No. Sorry?
For each week?
For each week, we have about 4 papers to present. Yeah. And if you want to contribute on 20 papers, you have to contribute, and you can miss about 4 of them during the 6 weeks, 3.5 paper almost each week you have to contribute. Okay? But the contribution doesn't need to be, something, long, It could be 2 lines of good example, or, a clear explanation of a concept which is not clear, or referring to, a paper which is missing here, and that's why we don't understand what's going on. Okay. So if there is no any other question, I'm going to start the lecture. So today's lecture is about regularization. And, in the previous lecture, we learned about backpropagation, which is the most popular algorithm for training in neural network and deep network. But overfitting is a big issue in neural network, and we have to take care of overfitting when we use backpropagation or any other technique for learning. And today we are going to learn different techniques for regularization. This include as simple as weight decay, which is quite old techniques, early stopping, using manifold hypothesis to generate more data or generate more fake data, adding noise to the input, adding noise to the weights, and dropout. There are many, an ensemble method, there are many different techniques to take care of this problem. So, but before I introduce any method, let me, there is a controller somewhere. I need to turn it off.
Could be that one.
No, this is mine. And I'm trying to turn it on here, but it's not working. We had the same problem the last lecture. You know, this controller is not working, but somehow we learned how to do it using this controller last week, but I forgot.
Those buttons there should definitely turn off the projector.
Yeah.
You want me to look at the...
You try to turn it off, and then start writing on the board. No, I mean, I meant, okay, that's okay, but I meant to mute it, not turn it off, because when you turn it on, you know, it takes a while. Yeah, but that's okay. Thank you very much. So we can take care of this later. So let's have, you know, a sort of general idea of regularization, have more in-depth insight about what's happening in general, not just for neural network, in general, what's happening when we are using data for training and what sort of problems we may face, and then we see how it can be handled in neural network or deep neural network. So general task in machine learning, in almost all of the machine learning tasks that we are doing is estimating a function. So we would like to estimate a function. Assuming that there's a true underlying function f of x, we are trying to estimate f hat. Okay? This is classification, it's regression, it's density estimation, almost all of the tasks. The main difference between different machine learning tasks is that when we are trying to find an estimation, we are choosing different function class, and we are choosing different ways of ranking elements of that function class, and we are choosing different ways of selecting one of the elements, or maybe searching in that function class. That's basically the main difference between different machine learning algorithms and techniques. So I have underlying function. I make some sort of assumption about the data. I choose a function class, and this function class could be class of linear, for example, classifier, all functions that can be expressed by a neural network. Then I have to rank those elements, and my rank would be based on my objective function, who is better, who is worse. You know, I have an objective function, the one which minimizes this is the best one, and so on. And I have a way to search in this function class and choose one, you know, my optimization technique. You know, I formulate this as a convex optimization, a non-convex optimization, gradient descent, and I go and pick one of them, okay? So this is sort of general scenario basically everywhere. And we would like this f hat to be as much close to f. Okay? Roughly speaking, you can always think that there is a relation between f and f hat and expectation of f hat of this form. So they make a triangle. We would like f and f hat to be close, but between f and expectation of f hat, usually there is a distance, which is our bias. And between expectation of f hat and f hat, there is a distance, which is our variance. Or if you want to be more precise, it's the square root of variance. And this variance plus square root of bias is the distance between f and f hat, which is mean square error. Yes. Yes. So, I have set of points, for example, and I would like to fit a function here. I may choose to fit a linear function. If I choose to fit a linear function, I have high bias. I'm far from the observation. But the variance is small, means on average, if I feed many linear functions, take the average of them, it's not that far from the one that I have fitted right now, that I have selected right now. It's not that far. But the bias is large. I'm far from reality. I mean, from observation, not reality. But if I choose, a function which is pretty flexible, I may have a very small variance, but I have a huge bias. Huge bias in a sense that each time that I fit a function, it's different from the previous one. And on average, this is going to be pretty far from what I'm fitting at the moment. So I have huge variance. Okay, yes?
Would it be the other way around? You have small bias? Sorry, large bias? Sorry. No, you said there would be large bias here, right?
Here, large variance.
Okay, sorry.
This is high variance method.
Low
bias.
Okay.
Yes. The linear case was high bias and low variance. Okay. So there's always a trade-off, and in order of minimizing this, we need to, understand, this trade-off and choose the right model. So if you look at the curve of learning, in all type of learning, you are going to observe, something like that. When this x-axis is the complexity of your model, this model is more complex than linear. A polynomial of degree 2 is more complex as compared to 1. A neural network with more, layers or more nodes is more complex to the one which has less. So to add to the complexity, a training error will decrease, and you can even make it 0. But the true error decrease up to some point, and after that start to increase, right? Which is basically, that's the right model, and after that we start overfitting the model. Okay, and intuitively, we learned what overfitting means in the previous lecture. Okay, so now let's make these concepts more precise and see mathematically what's going on here. So I'm assuming that the true function is f, the estimated function is f hat. I'm assuming that I have a set of observations. I have n observation, and this is my training set that I'm going to learn f hat based on this training set. And I make this assumption that my observations are basically a function of f, when f is my true function, plus some noise. Okay? And for simplicity, I assume that this noise is Gaussian noise. Centered at 0, sigma squared. So I have a true function from this true function on different data point xi. We have an output, but this output is not perfect when we observe it for learning. It has been distorted by some noise. Okay. What I'm interested in is the difference, for point x null, y null. What I'm interested is expectation of f and f hat. I want to make this small. F of xi, I will show it by f of I as well. So I want to make this distance small. Okay? But let's see what this distance is. F null is basically f plus some epsilon, right? So it is or let me start from here, actually. It's better. Let me, when we are trying to train a model, we have the observation, we don't have f, right? We are trying to minimize the distance between our observation and the prediction of the model. So I assume that the prediction of the model is the output of this function. So usually we are trying to minimize our observation and prediction of the model, right? But our observation is what? Our observation is f plus some epsilon. Okay? Minus y hat. Okay, is that clear what we are doing here? Okay, so let me expand this. This is going to be f null plus epsilon null squared plus y null squared minus 2 let me see. I will rearrange it this way. I take these two together and this one separately. So basically, imagine that it's f minus y null plus epsilon. So it's f null minus y null squared plus epsilon squared minus 2 f null minus y null.
Shouldn't that be y hat?
Yeah, there's a.
Yeah,
F hat null.
why not hat?
This is y hat, right?
Yeah.
Is that right now?
Shouldn't you just have your error term left? Because if you're not minimizing the error, so everything cancels except for the epsilon.
Sorry?
'Cause you're
I think, it's right now. This y was f minus, this y was f plus epsilon. Then I had y hat here. It's clear, it's more clear, We want to minimize this. This y is f epsilon, and this y hat is, I can either write it y hat or it's f hat. So then I have f hat minus f squared, f hat minus f squared. I have epsilon squared, and I have epsilon times f hat minus f. Okay? So basically, I can write all of this y hats as f hat now. Makes no difference, actually. Is it clear now? Yes?
Don't you need an epsilon in your last term?
Yeah, should there be an epsilon on the last term?
Yeah. Yes. Okay, is that okay now? Okay. So we have this expectation. So it basically it has three terms. It's expectation of f minus f hat. It's expectation of epsilon squared minus 2 expectation of epsilon times f minus f hat. Okay? So this is basically the term that I'm interested in, because I want the distance between the true function and the estimated function to be minimum. Yes? Sorry? Plus what? Where? This one is plus. So this is minus. How come? See, let me write it here again. So this is, I write it as y hat minus y squared. Okay? So y hat minus y squared. So it's what? Sorry? It makes no difference, it's a square. So it is f hat minus your y is f minus epsilon. Is that right? Sorry? Okay, we are doing this again. So this is right. Confirm. This because this is f plus epsilon, so it's minus f minus epsilon. So now I make a group. Then I have f hat minus f squared. I have plus epsilon squared. I have minus 2 epsilon f hat minus f. Sorry? Is that right now?
But yeah, different there.
Is it okay? No? Okay. Okay, this is the term that we are interested in, you know. We want this to be minimum, the distance between function and the estimation. So what's this term? Expectation of epsilon squared. Don't forget that this is standard normal. What is it? No, the expectation of epsilon would be 0, but expectation of epsilon is squared. So it's variance, basically, right? And minus this term that I don't know what to do with. Okay. Now, you know, I consider this case. I'm going to assume that this point is not in the training set. You know, this is correct for any point. Suppose that I choose a point that's not in the training set. If the point that I'm choosing is not in the training set, see what's going to happen here for this cross term. F hat is estimated based only on the point that is in the training set, right? I mean, F hat is completely independent from this set, this point, because I haven't used this. In fact, you know, if I look at this cross term, I can write it as, you know, this epsilon was y minus f. It is like y minus f, f hat minus f. And don't forget that f hat and this y are independent. So what this expectation is going to be, given that these are independent?
Multiple.
Sorry?
Multiple.
No. You know, this term is conceptually, this term is like covariance, right? Look at f as mean that has been distorted, and you observe y's. So y's minus its mean, and f hat minus the mean. So covariance between y and f hat when they are independent. It is 0, right? So in the case that the point that we are checking is not in the training set, this third term is 0. Okay? So if I summing up over all m points that are not in the training set, on the left, basically, I have summation of all of these points. Is equal to this summation plus I have, suppose that, you know, I have m of them. And I have m sigma squared, and this last term is 0. Here actually is the error that I care about. Here is the error that I'm measuring empirically using my data. So basically, I can conclude here that the error that I'm caring about is this empirical error minus m sigma squared, which is a constant. M sigma squared is a constant. It means that the error, the empirical error, is a very good estimate of true error if the point is not in the training set. You know, this is justification behind a cross-validation technique. In cross-validation technique, what we do, we are training our model using training set, but we have a validation set. Validation set is a set that our model hasn't seen. Validation set hasn't been observed, right? We are not minimizing the error on the training set. We are minimizing the error on the validation set. And we claim that the validation error is a good estimate of true error. That's the reason. Empirical error is a good estimate of true error up to a constant. That's not the case when it is a part of training set, though. We're going to see that case. But is there any question here?
Why minus m
Sorry?
squared? Why is it minus m sigma squared?
Why?
Yeah, why is it plus?
Because it's in this side, I take it to the other side. So what's happening in the most interesting or the more interesting case that this point is in the training set. That's the most common scenario. You know, we have a data set and we are training our model using that. And we are trying to minimize it. So in the case that this is a part of training set, this term, this cross term, is not 0 anymore. We can't claim that f hat is independent from the observation. So epsilon this is not 0 anymore. So we need to estimate this term. Okay? Actually, we can estimate this term under some condition. According to Stein's lemma, if you have if x comes from n theta sigma squared, so if x has Gaussian distribution, and if g is a differentiable function, actually it's enough if it's just weakly differential, then expectation of gx times x minus theta is equal to sigma squared times derivative of gx with respect to x. Okay, that's this expectation. Okay, let's apply this to our problem. You know, our problem is expectation of epsilon times f hat minus f null. So, you know, x here comes from n theta and sigma squared. Our epsilon comes from 0 sigma squared. So, you know, this is like x minus theta, right? Because theta is 0. And this is like gx. It's a function of epsilon. Because this f hat, f is not a function of epsilon, but f hat is. You know, if I change epsilon, f hat will change. So I can apply Stein's lemma here, and this is going to be equal to sigma squared derivative of g, which is f hat minus f, with respect to epsilon. Okay. So this is sigma squared is constant. But this actually, what does it mean? It's sigma squared, you know, and I have derivative of f hat with respect to epsilon, and minus derivative of f with respect to epsilon, which is 0. Because f is independent from epsilon. If I perturb epsilon, f will not change. F is the true function. F is my estimate. F has nothing to do with my observation. So if I change the noise of the data, the true function doesn't change. You know, true function comes before observation. But if I change the noise, my estimation will change. So this term is 0. I have only this term. Okay. And in fact, even you can write it as sigma squared f hat divided by y. If I perturb y, how basically the function is going to change, you know, because you know, if you're not sure that you can write it this way, you know, f with respect to epsilon, you can write it as f with respect to y times y with respect to epsilon, right? And y is f plus epsilon. So this is 1. So basically it's just f with respect to epsilon. So let me call it like d. So what is this? You know, what is this derivative? This derivative tells me that I perturb one data point, how much my function is going to change. So it's a measure of flexibility of your model. If the model is not flexible, if it's line, I perturb one point, how much this line is going to change? Very small or not, right? If it's quite flexible function, I perturb one point, how much this function is going to change? A lot, right? So it's a measure of complexity of the function that you are fitting. And if I sum over all points, you know, I'm going to have summation of yi minus, I erased that. It was, I think, yi hat minus yi squared on n data point that I have on the training set is summation over all of these functions plus n sigma squared minus 2 sigma squared di I equal 1 to n. Okay? So this is the error that I care about. this is my empirical error computed based on my training set. So empirical error, true error, is this error minus a constant plus this term. And this term has to do with the complexity of the model. So in this case, our empirical error is not a good estimate of true error. It's always biased downward, it's less than the true error always. So to have the true error, you have to add a component to this, and this component has to do with the flexibility of the model. So if the model is not flexible, it's a small. If the model is very flexible, it's large. And that's why we observe this curve. This is training error. The more complex the model is, this is smaller, but this is the true error. When complexity gets larger, this last term, the third term, for less complex models are smaller. So it's a small here. This term will be added to this. It's a small. At some point, it's large, and make a huge contribution here. So it make this one to raise, right? Okay. Is that clear? Yes.
I think that equation you should have an expectation on the right, because the left-hand side is a constant number, but the right-hand side is a random variable. The sense like
Yes, it's basically you have expectation here. True. Yeah. Thanks. So basically that's what's going to happen. Okay. So, and that's the reason for overfitting. In overfitting, what we are minimizing is this, empirical error over training set. What we really need to minimize is this, the true error. So one way to avoid overfitting is to add a penalty function to this. And this penalty would be an approximation of this complexity, which comes in many different forms. So we add a function such that this function is a small, this penalty is a small, for a small values of, for model of low complexity, and get larger with models of high complexity.
Like polynomial curves, mostly non-linear models, let's say.
Sorry?
Non-linear models would have high D.
Not necessarily nonlinear, Even when you want to fit a linear model, you can add a penalty here.
No, I meant that
This is nonlinear?
you said D will be large for complex models.
Right.
Like mostly non-linear models.
Yes, mostly nonlinear models, yes. Linear models are less complex. Okay? So this is the base of regularization. That's why in regularization we add a penalty function, So in regularization, we are minimizing we have a function which is our objective function. And this objective function is a function of parameters and function of observations. We are minimizing this over training set. That's the only thing that we have. But that's not enough, because if you do so, you're going to overfit your model. We're going to add a penalty function here. And this penalty function should be small for small values, for low complexity models, and large for high complexity models. Okay, so we are going to do regularization for neural network. It comes in many different forms. Now I show you that weight decay or regularization by L1 norm is clearly in this form, and I'm going to show you what's the effect of that on the solution. And then we'll see that even things like adding noise to the input is a form of this regularization. Dropout is a form of this regularization. Early stopping even is a form of this regularization. We're going to see that how it's a form of regularization, all of these techniques, and how does those methods going to affect the final solution. Okay. So before I switch to a slide, because I don't want to turn it off and on again, before I switch to a slide, let me just give you a view of regularization from Bayesian point of view. You know, this is mainly from frequentist point of view, but from Bayesian point of view, you know, you have basically what we are doing is to find the posterior of our parameters given data. So, and the posterior of our parameter given data is basically the data given parameters and our prior over parameter and marginal. So from Bayesian point of view, when you want to find parameters of your model, you're maximizing this posterior. Okay? So if I take the log of this, you know, because instead of maximizing this, I can maximize the log of posterior. So if I maximize log of f, this is going to be log of x1 to xn given theta plus log of my prior over theta minus log of marginal, right? But I mean, with respect to theta parameter, this marginal is constant, minus a constant. So this constant has no effect in terms of optimization when I want to optimize for theta. What is this term? Data given parameter. It's likelihood, right? Actually, it's log likelihood. And this is log of my prior. Compared with this one, you know, you may just work with likelihood, try to maximize likelihood. But you're going to overfit. To avoid overfitting, you have a penalty. This penalty is like a log of your prior. Okay? Not all penalty can be interpreted exactly this way. Some of them are exact. You know, if you penalize your objective function with L2, it's like having a Gaussian prior over your parameter. If you penalize your objective function with L1, it's like having a Laplacian prior over your parameters. But some of the priors that we have is not exactly, basically, some of the penalties that we have is not exactly our prior. Okay? So, but basically, we can view this like regularization from this point of view as well, from Bayesian point of view as well. Any question? Okay. Okay, so I explained this concept that, in most machine learning tasks, we need to estimate f of hat, and f of hat, we can basically add a penalty to our objective function and then optimize for that one. So the most popular penalty or the most popular technique in terms of optimization for deep network or neural network is what's called weight decay. Okay? So in weight decay, basically, we are trying to find weights of network using backpropagation, but instead of optimizing the cost function, which say, for example, is y minus y hat squared, instead of optimizing that, we are adding this penalty, the L2 norm of W, to the objective function, and then we optimize for that. Okay? I think it was a bad decision to open this because I'm going to get back to Blackboard now.
Turn off.
Yes, or make it mute or turn off. Okay, so we want to penalize neural network with L2, and my parameter is W, weights of the network, and the penalty that I'm adding is L2 norm of W. So I would like to make L2 norm small of W. Okay. So I call this J tilde of W x, y. So instead of minimizing J, I will minimize J tilde, right? In backpropagation, we used to take derivative of J using backpropagation technique. Now I need to take derivative of J tilde. And for simplicity, I just, maybe I write this. So which basically would be derivative of J plus derivative of this L2 norm. And usually I have a coefficient here would be alpha W. Okay. So I'm going to minimize this. What's going to happen? In my optimization, I had W minus learning rate times the direction of error, which was basically this term. I just need to add a coefficient of the W there. That's the only thing that's going to happen in the loop of when I'm trained. Okay. So why does this work? Why it's gonna prevent overfitting? So there's a intuitive and short answer, and there's a more mathematical and long answer to this. The short answer, and quite intuitive, is that this is my sigmoid function, right? If you don't have sigmoid function at the end of each unit, the whole model is going to be linear. Because if you think one layer to the other layer, it's like a linear transformation. You take input, you multiply it by matrix, which are weights, you go to the second layer. If you don't have this function, then there's another linear transformation that has been multiplied to this, and another linear transformation, and it doesn't matter. If you multiply 10 linear transformation, end of the day, it's only one linear transformation. So if you don't have this sigmoid function at the end of each unit, it's just a linear model. But we do have this sigmoid function. If I penalize large W's, means that I want my W's to be close to 0. I prefer small w's. Means I prefer the behavior of my sigmoid function when it's almost linear. When it's large, it starts to become nonlinear. So I don't want to let all sigmoid functions to behave completely nonlinearly. I want to, yes?
What's the difference between getting it to the operating trajectory and using a linear kernel?
Using, sorry?
A linear kernel.
A linear kernel for?
Just a straight linear line as a kernel. Because you said you want to keep it around the linear.
Yes. No, I mean, if it's completely linear, the whole model would be linear. So it's not neural network. It doesn't do anything. It's just a linear transformation. So you need nonlinearity. You need definitely nonlinearity. But you have to control this nonlinearity. You don't want this to be so nonlinear. You know, you want to control. Yes?
Do we normalize our x's so that like they're centered around
Yes.
0?
Usually, you know, in learning neural network, usually a good practice is that you always normalize your input right at the beginning, you know. Almost all the time, it's going to help. Okay, but so more precisely, let's see adding this term, how adding this term is going to change our solution, you know, not intuitively, mathematically. So to understand this, I'm going to write the Taylor expansion of this. You know, I'm going to assume that I have Taylor expansion of this and then see how this solution is going to be changed when I add a term to this. So for simplicity, I just write my objective function as a function of w. I don't write x and y because my penalty is just a function of w in this case. In some cases, it's not. Okay. So here, actually, I just write it as a function of w. So let's write a Taylor expansion of this. So what was Taylor expansion? If I want to estimate function f in the neighborhood of a, according to Taylor expansion, it's going to be fa plus 1 factorial plus f prime of a over 1 factorial plus f double prime of a 2 factorial. And sorry, there is like x minus a here, and there is x minus a squared here, and so on, right? So let's expand this function at w star. And w star, I assume, is the optimum solution of J. So let's assume that w star is the optimum solution of J. So this implies that the derivative of J at w star is equal to 0. I assume w star is the solution, means the derivative of J at point w star is 0. So if I write this expansion, so I have like a term like J w star, then I have derivative of J at point w star, which is 0. So the second term would be 0, because it's derivative of the function at point w star, and I assume that w star is my solution. Then I have this term, which is 1 over 2, and basically it's x minus a squared, means it's w minus w star squared, And don't forget that this w is a vector now, not a scalar. And second derivative of my function. Means second derivative means Hessian, right? So that's going to be this term. And I can expand it more, I can assume that there is a third term and so on, but let's assume that it's only 2 terms. So this is my approximation. Thanks. So this is my approximation of, so J hat is approximation of J. Okay? Now, here actually, this J tilde is what I need to optimize in rate decay. So J tilde would be this J plus this term. And in backpropagation, I need to take the derivative of this and derivative of this. Basically, derivative of J and derivative of penalty. So derivative of, instead of derivative of J, let me use derivative of J hat. So what is derivative of J hat? So this is J hat. So what would be the derivative? So I have derivative of J at point W star, which is 0. And I have the derivative of this term. It's quadratic. So it's going to be 2 times this 1/2, which is just 1. And it's going to be H W minus W star. Okay? So that's, sorry?
Why was that 0? The first derivative of J?
Why it's 0? Because we assume that W star is the solution of, is the optimum solution of our optimization. So if it's optimum solution of J, if it makes J minimum, that's the point that makes the derivative of J 0. Right?
One more thing. Over here you said that in accurate also we try to minimize the empirical error.
Right.
Basically we are minimizing the true error. So then you deduce something about overfitting. Like what was that? I didn't get.
Here,
Yeah, over here.
here actually I said that that's what we have access to, the empirical error. We can minimize this. But I just wanted to show that it's not a good estimate of the true error. What we are minimizing is not a good estimate of the true error.
Because of the 2 terms.
Because of this term. Because when you make it small, this becomes large. You can make it small by increasing the capacity of the function, the flexibility of the function. But the more flexible the function is, the larger this term is going to be. Okay, so that's my derivative. Now I have to basically substitute this here. So I'm going to use this derivative here. I need to set this derivative equal to 0, in rate decay. So it means that I need to set H times W minus W star plus alpha W to 0. So if I solve this, that's going to be the solution of my model after rate decay, given that this approximation is good approximation. Any question? Okay, let's solve for this. I have HW minus HW star plus alpha W equal to 0. I want to solve for W because W is my new solution. So it's going to be H plus alpha I times W equal to H W star. Okay. So W will be H plus alpha I inverse H W star. That's my new solution. Let me call it W tilde. So that's how my solution is going to change after weight decay. But if alpha goes to 0, alpha goes to 0 means that I don't have any weight decay, right? If alpha goes to 0, W tilde goes to W star, right? Because this is going to be 0, and it's H inverse H times W star. So W tilde is going to be W. So what if W is not 0? So what's going to happen if W is not 0? You know, H is a matrix. I can use singular value decomposition to decompose this matrix. And this is Hessian matrix. It's a symmetric matrix. So if I apply singular value decomposition, it's going to be Q lambda Q transpose because it's symmetric, you know. So these two are going to be the same. And you know, these Q's are orthonormal matrices, or eigenvectors of H transpose, and so on. So I'm going to I'm going to substitute this H here. So my W tilde is going to be Q lambda Q transpose plus alpha I inverse Q lambda Q transpose W star. Okay. I can write it as Q lambda plus alpha I Q transpose inverse. I just wrote this bracket this way. You know, I can do that because Q is orthonormal. So Q transpose Q is identity. As long as Q is not truncated, Q transpose is also identity. Okay? So I have here alpha I. Suppose that this alpha is, suppose it's Q lambda Q transpose plus alpha Q transpose I. Or QI Q transpose, makes no difference because it's identity. Then I can take this Q out. I can take this Q transpose out. And I can write it this way. Okay? So it's going to be just lambda plus alpha I at the middle. One Q has been multiplied from left. Q transpose is multiplied from right. So this is this term, and then Q lambda Q transpose W star. So this is going to be what? So the inverse of this matrix is going to be Q transpose inverse, when Q transpose inverse would be Q, right? Because Q is orthonormal. The transpose of orthonormal matrix is the inverse of the matrix. So it's Q, it's lambda plus alpha I inverse, and then Q inverse, which is going to be Q transpose, times Q lambda Q transpose W star. And then I can take this bracket out. So I have Q transpose Q here, which is identity. So W tilde is Q lambda plus alpha I inverse lambda Q transpose delta star. Okay. For the moment, suppose that I don't have this part. If I don't have this part, what's going to happen? I mean, or imagine that alpha goes to 0. If alpha goes to 0, then this is lambda inverse times lambda. It's going to be identity. So W star is going to be Q transpose W star, which is W star. So if lambda goes to 0, nothing going to happen. One way of thinking about this is that this Q transpose, since it's orthonormal matrix, it's like a rotation matrix. This Q transpose is going to rotate my solution. But then this Q is going to rotate it back to what it was. Okay? Now I have this term at the middle. But don't forget that this lambda is a diagonal matrix. This lambda, because we did singular value decomposition here. So this lambda is like lambda 1, lambda 2, up to lambda whatever, n, okay? So lambda plus alpha I has this form, right? You take the inverse of this. It's like this, right? And then you multiply this by lambda. So what would be a final multiplication of these two? It is like lambda 1 divided by lambda 1 plus alpha, lambda 2 plus lambda 2 plus alpha, and so on. Okay? So what's happening here is that this Q transpose take my solution and rotate it a little bit. Then for each direction, I'm going to multiply this by lambda 1 divided by lambda 1 plus alpha. And so if lambda I is greater than alpha, then lambda I divided by lambda I plus alpha is going to be 1. So if lambda I is greater than alpha, then on that direction, I don't do anything. I rotate my solution in that particular direction, that lambda is greater than alpha, this coefficient is going to be 1, so I don't do anything, I just rotate it back by this. But what if lambda I is greater or less than alpha? Then what would be this coefficient? It's going to be almost 0, right? We approach to 0. It's going to be a small value if alpha is large enough. So in the case that lambda is small, I'm going to rotate my solution in that particular direction that lambda is small. I'm going to shrink it to 0 and then rotate it back. So what these lambdas are, these are eigenvectors of Hessian matrix. Okay? So what does this lambdas tell me? If lambda is large, means that I'm basically considering a direction in which changing in that direction is going to change my objective function significantly. It's a direction with a large eigenvector, a direction of Hessian matrix with large eigenvector. So it's going to significantly contribute in minimizing my objective function. If lambda is small, it means that in that direction, moving in that direction is not changing the function significantly. So basically, weight decay keep the directions that change the function significantly, shrink directions that do not contribute significantly. Okay? Keep only some of the directions. So there is a concept which is called effective parameter. So effective parameters in neural network and weight decay is lambda I divided by lambda I plus alpha over all I. So this is called effective parameters. So you can see that some of these are going to be 0, right? Originally, if I goes from 1 to n, I had n of these values add together. Now, for large lambda i's, I have 1. For a small one, I have 0. So the number of parameters is less. So that's why weight decay helped to avoid overfitting, because it reduced the number of parameters that I have. It reduced the complexity of the model. The larger the alpha is, the smaller this effective parameters is going to be. It shrink it more. Yes?
So when you do this technique, essentially what you're doing is just making a lower rank approximation of your solution, right? You're cutting out some of the singular vectors. So is just using a lower rank or a lower dimensional parameter vector equivalent then to using a high dimensional parameter vector with regularization? Could there be any?
But the parameters vector, the dimension of parameters vector has to do with the number of units that you have. So lower dimensional vector means less number of units, which definitely helps to avoid overfitting, right? If you have less number of units, the dimension of W is less. And yeah, definitely less number of units correspond to lower, less complex model. So it helps overfitting. But our problem with neural network is that quite often we don't have any systematic way to choose the structure of the model. I'm going to decide that in the first layer I have 5 units, and the next layer I have 10 units, and then I have 20 units. And I don't know, it's more or it's less, or it's too much, or I have too many, or I have to choose less than that. I'm not sure, right? So it's more, I mean, there are more systematic way to fix the structure, still somehow avoid overfitting by controlling, say, for example, the size of the weight, rather than playing with the structure and, you know, see if it overfits, you know, change the number of units. But if you change the number of units, it works definitely. But it's going to be pretty hard to, you know, play with the number of units to make it less complex. But it has the same effect, as you mentioned.
Essentially, if you're trying to pick the best rank of your solution, which means the number of connections in your network, that's kind of like cross-validation to choose what your lambda parameter, or sorry, your alpha parameter should be. It kind of achieves the same thing in the end, but it may be harder to do the first.
You remind me of something interesting. Maybe I talk about it in the next part of lecture after the break, or we can talk about it offline. This derivation that we had at the beginning of the course, I have an idea for a final project for controlling the complexity of the network based on this derivative. This derivative was derivative of the final output of the function when you perturb one point. So maybe we can compute this derivative using backpropagation sort of technique. You know, the way that we use backpropagation to find the derivative of objective function with respect to weight. Maybe similar approach can be applied to compute that derivative and use that for basically estimating the true error rather than just training error. Let's talk about this later. Yes?
So I'm wondering for this here, if we have quite a few parameters that basically goes to zero, considered zero, that doesn't reflect that our rate weights are zero, right?
No.
Okay.
No. If you penalize it with L1, then those weights become zero, really. But here, no, it's just a small value.
Can we think of it sort of like a print supervised principal component in a way? Because we're trying to get some things to,
I don't see the direction, but
it's a tangent.
PCA is kind of similar, right? PCA is just like a single valued composition. You
Okay.
can do some basis.
Yeah, basically.
It's the same thing.
yeah, in this sense, it's true that in PCA you're rotating your coordinate system toward the direction that are more important. But I didn't see the direction with supervised PCA. Maybe you can explain more to me after the break. Any other question? Okay, let's come back at 3:45.